let's take a look at Euclidean domains. Roughly speaking, a Euclidean domain is an integral domain in which we can perform division with remainder. But to do so, we need some way of measuring the elements so that we can decide when we have a remainder. Now, in the case of the integers, if a and b are integers, then there always exists q and r, for which b equals qa plus r, and r falls in this range. R is the remainder, q is the quotient. We recognize r as a remainder because it falls in this range. It's either equal to 0 or it's somewhere between 1 and a. Speaking more generally for integral domains, we need a norm function to measure, you might say, the size of elements so we can define remainders. Let R be an integral domain. A Euclidean norm on R is a function delta from the non-zero elements of R to the natural numbers, for which delta of A is less than or equal to delta of A times B for all non-zero elements A and B in R. Now, if you've seen this before, you may have seen a slightly different definition of Euclidean norm, and I'll discuss that a bit later. So just bear with me on this definition. R is a Euclidean domain if there is a norm, delta, a Euclidean norm. I think it's just often just called a norm, for which the division algorithm holds. And what that means is given any a and b in R with a non-zero, there's a q and a little r in R, for which b equals qa plus r, and r is 0 or the norm of r is less than the norm of a. Now, we refer to q as a quotient and r as a remainder, just as we would for integers. We are also going to say, and I don't know if anybody else does, that a pair, R delta, is a Euclidean pair if R is a Euclidean domain and if delta is a Euclidean norm on R. Now I need to make two observations. First, if R delta is a Euclidean pair, then there are actually, so R is a Euclidean domain, there are actually infinitely many distinct Euclidean norm functions. Delta is not the only one by any means. What we can do is we can take a positive integer and inflate delta. So delta sub m of a is m times the original delta of a. That's also a Euclidean norm. We could also add m, and that still gives us a Euclidean norm. So we get additional Euclidean pairs. The only purpose of this notation is to identify delta as a particular Euclidean norm on the Euclidean domain R. That's all its purpose is. The other thing I need to mention is that there's no requirement in the division algorithm that quotients or remainders must be unique. And we're going to discuss that issue at some length a little bit later. Okay. And the result may surprise you. Some Euclidean norms are multiplicative. We've seen this concept with some of the quadratic norms. norm of the product is the product of the norms. Not all Euclidean norms are multiplicative, however. The integers form a Euclidean domain under the multiplicative norm delta A equals absolute value of A. If F is a field, then the polynomial ring is a Euclidean domain under the non-multiplicative degree function. It's also, by the way, a Euclidean domain. Well, I shouldn't say it that way. It's a Euclidean domain, period, because there is a Euclidean norm. But there is another Euclidean norm, and this one, I called it epsilon. Epsilon p of x is 2 to the degree of p of x. This is a multiplicative Euclidean norm. So here we have an example of a Euclidean domain that has multiplicative norms and non-multiplicative norms. Note that if R is an integral domain, and if a function n from the non-zero elements of R to the natural numbers is positive, which means n of R is greater than 0 for all elements of the domain, and if n is also multiplicative, then n is a Euclidean norm, because if a and b are non-zero, then multiplicativity gives us this, and because the norms are positive, that's bigger than or equal to norm of A. Now that doesn't make R a Euclidean domain. It doesn't make this pair a Euclidean pair because we have to check the division algorithm. That's part of the definition of a Euclidean domain. So speaking about that, something might have occurred to you. We've seen, at least in some special cases, that this quadratic domain, where n is a square-free positive integer, we've seen the cases n equals 1, 3, and 5, these quadratic domains have a positive multiplicative norm. So n is a Euclidean norm on R, and we are naturally led to wonder which of these quadratic domains are actually Euclidean domains by virtue of this Euclidean norm. What's missing is, or another way to say this is, which of the pairs Rn are Euclidean pairs, namely which have the division algorithm. Well, to explore that, let's take a equals 2 and b equals 1 plus square root negative n. The Euclidean algorithm, the division algorithm, requires, there should be division, Euclidean algorithm is something else. We'll get to that. The division algorithm requires the existence of a quotient and a remainder for which b here is 2a plus r. So we're dividing b by a. R is 0, or the norm of R is less than 4. But R cannot be 0, and I'll let you ponder that. So the norm of R is less than 4. If I write Q as x plus y square root negative n, R will then be b 1 plus square root negative n minus 2a, minus 2q, this a is 2, and that looks like this. And this is the norm of R. It must be less than 4. But neither of these can be 0, and so the norm of R is at least 1 plus n. So 1 plus n has to be less than 4. So n has to be 1 or 2. These are the only possible candidates. Or put another way, the again, division algorithm does not hold when n is bigger than or equal to 3. So we have to consider the cases n equals 1 or 2. And let a and b be in the integral domain with a non-zero. Excuse me. As shown in this figure, the complex number b over a, if we're just looking in the complex plane now, not just in the integral domain or quadratic domain, the complex number b over a lies in one of the rectangles, could be on the edge, that's formed by 4 r lattice points. So x plus y squared negative n is in R, so is this one, and this one. B of A is inside one of those rectangles, let's say this one. Therefore, the maximum value of the shortest distance between B over A and an element of R, the maximum shortest distance will occur when B over A is right smack in the center of this rectangle. And that maximum shortest distance would then be, so B over A would then look like this, x plus 1/2 plus y plus 1/2 squared negative n. And to compute the maximum value of the shortest distance, you might say the worst case scenario for the shortest distance, since that happens when B over A is smack in the center, we can use any 4 of these to compute that distance. We may as well use x plus y squared negative n. This is the difference between the so Q is this bottom left vertex here, the lattice point of R, and the maximum of the minimum of the square of the distance is this. We subtract and square. That's equal to 1 plus n over 4, which is less than 1. So the maximum shortest distance is also less than 1. So if r is not 0, then we have, by taking q to be the closest element of r to b over a, norm of r is norm of b minus qa, which is this absolute value squared. Factor out absolute a squared. We get this thing we've been dealing with here. That's less than 1. And so this is less than absolute a squared, which is the norm of a. So the norm of r is less than the norm of a if r is not 0. And the Euclidean algorithm, again, division algorithm, I guess I have Euclidean algorithm on the brain here, which is odd because I almost never use it myself. So we have the division algorithm. So in summary, if n is a positive square-free integer, among these quadratic domains with this norm, these pairs are Euclidean pairs if and only if n is 1 or 2. So r is the Gaussian integers, or z plus c square root negative 2. We should discuss a possible point of confusion concerning the division algorithm for the integers. As I mentioned earlier, the definition of norm does not state that the quotient and the remainder must be unique. So, for example, in the integers with this Euclidean norm, we can write 5 equals 2 times 2 plus 1, and 5 equals 3 times 2 minus 1. And in both cases, the norm of the remainder, either positive 1 or negative 1, is less than the norm of the divisor, 2. So, both 1 and negative 1 are remainders according to the definition. However, for the integers, a more common form of the division algorithm states that for all integers a and b, there exist unique q and r, for which b equals qa plus r, where r lies in this range. So this says a little bit more about remainders. It says they're either 0 or positive and less than the norm of a. Okay. Not to say that a is not 0 here, but I guess you figured that out. So I'll add that. So this more common form of the division algorithm does not conform to the definition of a Euclidean domain. That's the way it is. And I'll return to this issue of uniqueness of quotients and remainders later. And as I mentioned, I think there's going to be a rather surprising result. Actually, the definition of Euclidean norm varies quite a bit among authors, and not always equivalently. So that's somewhat of a problem. There was a paper whose reference I give at the end of the book, in which the authors describe in detail a dozen potentially reasonable candidates for the definition of Euclidean norm. And they discuss which of these dozen possibilities actually work, and there are 7 of those, and which are stronger than others and which are equivalent. So there's quite a bit of variation and therefore potential confusion about the definition of Euclidean domain. Just to give you a couple of examples, some authors do not require this condition. It's defining a Euclidean norm simply as any map from the non-zero elements of the integral domain to the natural numbers. In the exercises to this book, I ask you to show, and I'll give you some help, that if the division algorithm holds for such a weak-looking norm, any function, there is also a norm by our definition on this integral domain R, making that an Euclidean pair. So this condition that we include, and many authors include, actually adds nothing other than very considerable convenience to the definition of Euclidean norm. Okay. We use this condition quite a lot, and it seems surprising that you actually don't need it, okay? Or you don't need to include it in the definition of Euclidean norm. Another example, some authors allow the norm to be real valued rather than n valued, n being the natural numbers. And there's another exercise in the book where I ask you to show that this does not increase the collection of Euclidean domains. You get no additional Euclidean domains other than what you would get under our definition. And that's because any R-valued norm can be replaced by an N-valued norm. Finally, here is a theorem I leave the proof to you. We've seen a couple of examples of this. If f is a strictly increasing function on the natural numbers, then the pair R delta is a Euclidean pair if and only if Rf composed with delta is a Euclidean pair. So you can, in some sense, inflate any Euclidean norm. If you do it properly, you get another Euclidean norm.